video is about using functions involving e. The operations in this video are going to involve a number called the natural base e. It's a constant in mathematics, similar to like the number pi, which is a constant, 3.14159, etc. The natural base e is also a decimal that never ends. It's approximately, as you can see written over here, 2.71828 and so on and so forth. It never ends either. The natural base e has nothing to do with circles like pi does. The natural base e comes from the value of this expression as n gets bigger and bigger, or as n approaches infinity. And if you look at that expression, if you're familiar with compound interest formulas, remember n is that number of how often is your money being compounded each year. So if it's compounded quarterly, the n stands for 4. If it's compounded daily, the n stands for 365. So mathematicians started looking at, well, what if it's compounded more than daily? What if it's compounded twice a day or 3 times a day or every minute of every day? And as n gets bigger and bigger, the value of that expression approaches this number e, 2.7182 and so on and so forth. And so they've given it a name. It's called the natural base, and it comes up in exponential and logarithmic equations a lot, and that's why it's part of this chapter. So we're going to start by learning how do we do things with e. For example, how do we simplify expressions where e is the base? You treat it just like an or a variable when you've got exponents on it. So you're just going to basically be using your exponent rules. You're not going to take out a calculator and actually figure out what this expression equals. It's just e to the second times e to the fifth, and we want to simplify it as much as possible. See if you can get it to be one exponential expression. With the base of e, the exponent would be 7, because we have to add our 2 plus our 5. That's just a rule of exponents. So we're really just practicing our exponent rules at the start here. So the 12 divided by the 3 we simplify as normal, which is going to be a 4. And remember, you've got an exponent on top and an exponent on bottom with the same base. You subtract them. So e to the 4 minus 3 power is e to the 1. And no, you do not need to show that 1, but I'm putting it there so you can see the math that I did. Remember, if there's an exponent outside a parentheses, it's going to come in and affect all of the exponents inside. So the 5, which currently has a 1 on it, becomes 5 to the second power. And the e, which currently has a negative 3x, becomes a negative 6x power. And then we just have to simplify this expression. 5 to the second power is 25. E to the negative 6x is, well, it's e to the negative 6x. Since we don't know what x is, x could be positive or negative, we don't actually know whether this is a negative exponent or not. So you might see it written like this, or you might see it written like this, and either answer is acceptable. When it's e to the negative 6x power, that's not technically a negative exponent because we don't know x. But either of these answers would be acceptable for full credit. Be forewarned that you may have an example like this where one of the exponents has an exponent and one of the exponents does not. So if this exponent on the bottom is just a 1, then when we simplify this, e to the 4x minus 1. We're taking our exponent from the top, we're subtracting our exponent from the bottom. The 5 doesn't have anything to simplify with, and so that just stays on the bottom. So you may see it written like this, which is kind of cumbersome and ugly, or you might see it written as a 1/5 times e to the 4x minus 1. There's really nothing more we can do to simplify that expression. Just wanted to show you an example. In case you're given an example like that, just do as much as you can. It may not look any more simple to you, but it is a simplified version. Always must combine if the bases are the same. Always must combine to simplify to your final answer. Apply your properties of roots and radicals as well. So we're not just practicing our exponent rules, but also our radical rules. So it looks like we have a square root here. We've got things with e on the bottom, things with x on the bottom. I think maybe we'll simplify what's inside first and see if that helps us. So not doing the root yet. We're going to leave the root alone. We're going to simplify what's inside. It's a fraction. So we've got 27 and 3. It's going to simplify just 9. We've got e to the 11th and e to the 3rd. Remember, we're going to subtract the exponent on top minus 1 on bottom, so it becomes e to the 8th power. And we've got x to the negative 4th on top and x to the 2 on bottom. So we're going to take x to the negative 4 and subtract 2, which ends up being x to the negative 6th. Okay? I'm going to rewrite what's inside here, because I know I can't have any negative exponents. And so I drop it to the bottom and make it a positive exponent. And now I'm going to deal with my root. Now that I see that everything in here actually has a perfect square root, everything's going to come out in even groups of 2. I'm going to just do the square root. So the square root of 9 is 3. The square root of e to the 8th is going to be e to the 4th. And the square root of x to the 6th is going to be x to the 3rd. And there's no root left over. So this is my final simplified answer. You can also graph functions that have e as the base. So this is just an extension of what we already know about graphing exponential equations. How do I know if this is an exponential equation? Well, I've got a whole bunch of numbers, and my variable is x, located up there in the exponent. Remember that e is not a variable. E is just a constant. It's approximately 2, right? So e is a constant, 2.78 or whatever it equals. And it's being raised to all this exponent, and that's where your variable is. It's in the exponents. This is an exponential equation. I'm going to make my table. The values that I use for an exponential equation are -2, -1, 0, 1, and 2. Remember, my method for graphing these is just to deal with any multiplication that's there and the exponent that's there. Do not deal with any horizontal translation on the table or vertical. These get dealt with on the graph. This is a horizontal translation that we're going to shift all of our points 2 units to the right, because it says -2. And this one's vertical, which tells us we're going to shift all of our points 1 unit up, because that's a vertical translation of +1. All right, when I plug in -2 as my exponent, I am evaluating e. I'll just show you here what I'm doing. I'm evaluating e to the -0.75 times -2 power, right? It's not going to be a pretty number. You have to find the e button on your calculator, which is usually located in the area of your exponents, your x to the 2nd power, your logs. You'll find a little button that usually says e to the x. And when you type that in, it pulls up e, and it asks you what exponent do you want to type in. So we'll type in -0.75 times -2. And when you hit enter on that, it's going to give you a pretty nasty decimal number because we know e is a decimal. So we're just going to be approximating this on our graph. And on my table, I'll fill in to the nearest 100th, even though there's no way I can get to that degree of accuracy on my graph. So it's just going to be close enough. When we do this one, it's e to the -0.75 times -1 power. So I find that e button on my calculator again. I change my exponent to -0.75 times -1. And the calculator tells me that's approximately 2.12. E to the 0 power is going to be 1, so there's a nice whole number. E to the -0.75 times 1, evaluate it on your calculator. It's approximately 0.47. And then e to the -0.75 times times +2, and that comes out to 0.22. Okay, so I see that my numbers are getting closer and closer together, my y values, without ever becoming negative. I'm going to take all the values from this table, find them on the graph, and then don't forget to shift them 2 to the right and up 1. So I'll find my first point at -2 and then approximately 4.5. It's okay if it's approximate. Go 2 units to the right and 1 unit up. Put that on the graph. Find my next point at -1 and then a little bit past 2. Go 2 units to the right and up 1. 0.01 and then over 2 units to the right and up 1. That should be exact. 0.1 and then about a half over 2 units to the right and up 1. And then the 0.2, 0.02, which is just a tiny bit off of the x-axis, over 2 and up 1. As you can see, they're getting closer and closer together, and they're approaching my asymptote, which is located at, remember your asymptote moves with the vertical shift, or with k. So we've got our asymptote located here. I like to draw that first when it's not the x-axis, so I know what line I am approaching, and I'm never going to touch it or cross it. So for the domain here, we've got x being all real numbers. For the range, we have y being greater than 1, because we have an asymptote that's located at y equals +1. So it works just like every other exponential growth or decay function. Well, if the base is e, it's an exponential growth function because our base is greater than 1. So it works like every other exponential growth equation using the same things on the table. It's just going to be decimal, so it's kind of an approximation. And then, just like all other exponentials, we've got word problem applications. So an exponential growth model with E in it specifically is used when money is compounded continuously. Okay, so this is, instead of being compounded daily or monthly or quarterly, like I was explaining at the beginning of the video, what if it's compounded every second of every minute of every day? Then we can't figure out what n equals, because n would be like infinity, right? Because it's not going to just be 4 times for quarterly or 365 for daily. It's going to be an infinity. And so we use a new formula that involves e, because we know e comes from that expression. So the new formula that involves e sometimes is written as this: y equals p times e to the RT power. The p here stands for principal, which is your starting amount. So it's not different from the formula we've been doing. They've just changed the letter. It stands for principal because this is specifically applied to money problems. And a bank would call the amount that you put in the account at the beginning, they'd call that your principal balance. So principal is your starting amount in the bank. We know E is just the constant E, which is approximately 2.78. We've got R is now an exponent. That's our percentage. Don't forget to express it as a decimal, being multiplied by T, which is time. All right, and let's see this in action. So for example, you deposit $2,500 in an account that pays 5% annual interest compounded continuously. When you see those words, that's how you know that you need to use the formula that's got E in it. P times E to the RT. And so we're going to find the balance after 2 years. So our model would be y equals principal amount or starting amount times E to the R. Don't forget to write your percent as a decimal. T power. Remember, a model has 2 variables in it. Then I'm asked to use this model to find the balance after 2 years. So y equals starting amount times E to the 0.05 times 2 power. And when you evaluate this on a calculator, just be careful with the way you're typing it in. You have to do the exponent first and then multiply it by 2,500 at the end. So 2,500 times E to the 0.05 times 2 power. Because this is money, we're going to round to the nearest hundredth and figure out the balance in our account. It's $2,762.93. And if you compare this to compounding daily or compounding monthly or something, it's just going to be slightly more. You actually end up with slightly more money in your account if it's compounded continuously, every second of every minute of every day, because they're actually paying you more frequently, paying out your interest more frequently. And that is all.